Okay, thank you all very much for coming. This is about second order science. We have a guest here from Vienna, Austria, Karl Mueller, and he and Alex Riegler have produced a special issue of the journal Constructivist Foundations, where they requested several target articles. I wrote one, and other people wrote some, and then they asked for comments on the target articles, and Mark Materno wrote a very nice comment on my article, and then the authors of the target articles were allowed to reply to the comments on their articles. So there were a number of people who participated in this endeavor, but there are only 3 of us here today, but still 3 is better than 1 or 2. So Karl Mueller will be our first speaker, and then I will speak, and then Mark will speak, and then we'll have a general discussion. And you will find that there are sort of basically 2 different conceptions of second order science. And I think they can be most easily explained by knowing the biographies of Karl and me, where Karl was for several years the operator of a large social science database in Vienna, Austria. And so he gathered up data from studies being done and archived it and then tried to make sense of it all. And he developed some methods for combining these independent studies into more robust knowledge. And even designed a doctoral program to teach people how to do this sort of second order science. My interpretation of second order science was influenced by my mentor at the University of Illinois, Heinz von Foerster, who said that the observer should be included within the domain of science. And then it seemed to me that also scientific theories were having an effect on social systems. So I suggested adding 2 dimensions to the conception of science. And then there's some other things that are going on. So that's the sort of main difference, that Karl focuses more on data interpretation and analysis. This is my explanation. And I am a little bit more interested in the philosophy of science. So let's listen to Karl, and then we'll proceed from
there. First, thanks to Stuart and to Mark for inviting me here. I should start by also emphasizing that when Stuart says something about second-order science, and I say something about second-order science, we talk about very different things. So that's a common point. There's a strong disagreement with respect to introduction. It was definitely not on the reasons of the data archiver, so that I came up with this idea of second-order science, but this had different reasons. It had to do with some science studies and so on. So at least in my understanding, I wouldn't accept this data interpretation. And you are not hearing to something about metadata or things like that, but okay. I start with something Stuart and I have in common, and that's I would call Heinz von Foerster also my personal mentor. And I learned Stuart had the privilege of studying with Heinz in the 70s, and I met him in the mid-80s and developed a very intensive cooperation. And so that's one of our common reference points. I would like to introduce you with some sort of new architecture about science in terms of science levels. And you hear something about different ways of combining the magical number 2 with science, and then I will talk about second-order science as we see it in this journal, which unfortunately I couldn't bring the printed version with me because that's still not printed and will be available only next week. So that's the 4-part program, and I tried to be short. That's our common mentor, and he did something very bad, at least for us. He introduced the term second-order cybernetics in a huge book in the year 74. cybernetics of cybernetics, and on the front page there was already the definition. First order cybernetics is cybernetics of systems observed. Second order cybernetics of observing systems. And then you would expect in a 500 or 600 page book several hundred pages on second order cybernetics, but in the entire book there's only 2 pages on second order cybernetics, and they were written by Stewart. So who was he was responsible, and there's only a 4-page article by Heinz on second order cybernetics, which can be found in his in this collection of articles, Understanding. So he developed something. He said it's a huge revolution. It's a Copernican revolution. Can only be compared to the impact Copernicus had, and with respect to the scientific method. And it was a Copernican revolution without traces.
So you're trying to tell us that the idea doesn't go very far.
I'm simply telling you something about a mystery for me and probably for us, and you won't be. We have the Heinz von Foerster archive in Vienna. We haven't found any secret paper. So what I really mean by second order cybernetics and so on. So that's he introduced it, but generated some sort of mystery because. But somehow this notion of second order was around, and this was important now for Stewart and myself. I'm not going, due to time restrictions, into what could be parts of building blocks of Heinz von Foerster's vision. I'm going to this one, this diagram, to what I would call a 3-level differentiation of science, and something which is rather of modern origin. So the 3 levels, in my understanding, started somehow by the 1950s and are now fully developed, except for the second order level, which is still propagated by me and a few others. But I would, since Mark titled his presentation, "Do we need second order science?" I want to ask 3 questions. Do we need first order science? And first order science is science as we know it. That's a science of exploring the world, exploring societies, and building up technological systems, building up the possible worlds of logic, mathematics. So that's first order science. And until 1900s, all of science was first order science. And do we need first order science? Definitely yes. And probably there's no one in this room who would have strong objections to first order science. So this is something we have and something we need and something which we hopefully can accept that this is a necessary level in this 3-level differentiation. Now, I come to this 0-order level. And this 0-order level, and this has something to do with my background on databases and so on. In the last decades, one saw the emergence of partly large-scale research infrastructures across all science fields. And it's not a small thing anymore, and it's not marginal. And in Europe, we have now a new wave of research infrastructure facilities, and it's at least more than 30 or 40 billion euro, which are being spent in the next years in the construction and building up and also maintenance of these research infrastructures. These research infrastructures can be found in physics, in biology, in the social sciences. And in the social sciences, for example, there is a big European data archive, which is now qualified as European research infrastructure. And you have in this, there's a so-called S3 process. S3 is a European strategy forum on research infrastructures, where between the different nations they negotiate which infrastructures are being built and financed and so on. And so they are planning a huge telescope. There's a polar sea vessel, there's a sea observatory, and there are information databases for biology and so on. So there are all sorts of big research infrastructure projects being built apart from the existing one. The first big facilities in Europe came into being in the 50s. There was CERN in Switzerland. There was the big center in Jülich in Germany and so on. So since the 50s, we have this zero-order level. And this zero-order level has very important functions also for first-order science. And in working very long on these things, I think that the term catalytic function is most appropriate. A catalytic function means the results or the output of this zero-order science level, they enable things. So by having CERN, for example, you can do certain experiments which are important for testing, and you couldn't do certain tests without these facilities. So they enable first-order, different versions of first-order research, and or they accelerate first-order research. So, for example, by having large bibliographies and so, bibliography databases and so on, you can find relevant articles in a very short time, and you don't have to go to all the libraries and other sources and to do this. So yeah.
So this would include like what they call computational science now, the ability to navigate through all of this stuff?
It's so tools to navigate through these things. Yeah, they are not part of a research process itself, but they help you and they have fulfilled this catalytic function. And so we have this level of research infrastructure, the zero-order level, as I call it, and the question, do we need this level? And I would say, under all circumstances, yes. That's becoming more and more important. And we can expect that maybe 20% of science funding in the future is devoted simply for the maintenance or building of new research infrastructures. So that's quite a significant part of, to support in this catalytic function, enable first-order research, you have this first zero-order level. Now, if one looks at these the science landscapes around the 1950s, 60s, there's big science as a new phenomenon. On the first-order level, there are these first buildings, constructions of large-scale research infrastructures. And at this period, I would qualify philosophy of science as it was developed during these years as belonging to this second-order level. Now, talking about the magic number 2 and science, I would like to address the phenomenon that we have 3 very similar notions of combinations of 2 with science. There's something which I developed with a colleague of mine, Rogers Hollingsworth. He's a sociologist, historian of science. In several articles, we made this distinction between science 1 and science 2. Science 1 is the organization of science from its beginning to up to 1900, 1950, and science 2 is the cognitive organization of science, which differs in all sorts of respects from the previous form. And one interesting reference point for this distinction was also Friedrich von Hayek. He wrote a wonderful article on the nature of complex phenomena, where it's absolutely worthwhile to read it, where he talked about the difference between theoretical physics or classical physics on the one hand and biology, and that in classical physics and he made all sorts of distinctions which we can also be found in our science 1, science 2 distinction. So the leading field of science 1 is theoretical physics. For science 2, it's the life sciences. For science 2, it's a complex phenomenon. And one concept which was very important for Hayek is the concept of pattern. And life sciences are focused on patterns and pattern recognition, pattern construction, and so on. So this is one differentiation of science. The second one, which can be found in the literature, is Science 2.0. And this is built after the Web 2.0. So that's the main emphasis here is that for cooperation, collaboration in science, we have now all sorts of new tools, web-based tools, and Web 2.0 focuses on these cooperation possibilities, which are no longer face-to-face, but web-based and with several tools for communication. So that's another science and two distinctions. But what is second-order science after we have all these tools? In my suggestion, what second-order science is it's the science which deals with problems which are generated through re-entries. And re-entry is an important notion in Spencer Brown's laws of form. And Luke Kaufman, who is a mathematician and very much acquainted with the work of Spencer Brown, he uses this notion of re-entries in the following way. This comprises things like computation of computation, cybernetics of cybernetics, geometry of geometry, linguistics of linguistics, logic of logic, magic of magic, mathematics of mathematics, pattern of pattern, teaching of teaching, will of will, and I mean, one could continue with this list for a very long time. And the characteristic operation for these second-order sciences are you have a certain building block, very abstractly formulated, building block from first-order science. And this can be a theory, this can be a theoretical concept, this can be also a field like cybernetics or sociology and so on. And then you perform a re-entry operation on this building block and you create this X of X. So that's then sociology of sociology, for example, evolution of evolution, evaluation of evaluation, whatever. So you create a second-order problem by performing this re-entry operation of a first-order science building block. And then these building blocks can be inputs to first-order science, like theories or models, can be outputs, like you have maybe one way to help this. You have, for example, meanwhile, an extremely well-developed area of meta-analysis in psychology and medical research. So if you have a lot of clinical tests of drugs, they all performed in roughly the same way. And since the 80s or so, you have a growing number of meta-studies. You take all sorts of tests and make a test of tests. And the advantage of these tests of tests is you have much larger samples. You can correct biases and can all sorts of things to improve outcomes due to this collecting of various first-order tests, and you do this meta-analysis, or in my terminology, you do this second-order analysis, and you create more robust results when compared to the first-order tests alone. So that's the characteristic operation, and that's also the major departure between Stewart and I. For me, that's the defining characteristic of second-order science. For Stewart, he will talk about his one later, but it's observer-related. Therefore, I come to the conclusion that the second-order level constitutes also a vast and largely unexplored science frontier. There are a lot of problems, a lot of very challenging questions along these re-entry operations. And so one point which I make will be very briefly, but only, and in this example it relates only to the social sciences. The argument is as follows, that in the 19th and 20th century, social sciences were able to explore the world, so there was a lot of novelty in terms of approaches and so on. As social sciences became institutionalized for a longer and longer period, social sciences in their explorative mode lose some of their innovative impact. It becomes more and more difficult to become innovative in the social sciences because they operate now for a very, very long time on societies, but it becomes more and more interesting to look at what social scientists have produced and to make this second order exploration, and you come up with probably a lot of new and interesting insights. I'll give you just one example, because then we'll conclude to give opportunity to the other speakers. If you evaluate for a big university or the Academy of Science, you have evaluated 9 times already, and you order now a 10th evaluation. The 10th evaluation will add very little novelty to the previous 9 ones. But looking at the previous 9 evaluations and systematizing them and ordering them, and unfortunately don't have time to present some sort of general methodology how you do this, but looking at the 9 previous examples, you will detect a lot more insights and novelty and innovation than by adding a 10th. So we have this inversion of novelty in a lot of social science areas, and there are different types of reentries. I come now to the conclusion. You can, the upper example would be of the clinical and psychological test, where I have a narrow field, first order fields, and then you have a lot of instances for this, or you can find your first order building blocks, and they are distributed across a lot of science fields. And I would like to conclude at this place, at this point, with the following general claims. There are, there's this catalytic function for first order science, and therefore zero order science. Therefore, we need zero order science. And there are 3 major functions which second order science has. And the first function is, which I already said, that this is an innovation function. It provides innovation outlets and can act as a sort of innovation pump, because most of the area of second order science has not been explored so far. The example with psychological and clinical tests shows that it can also have the function of providing more higher robustness in knowledge due to bringing the test and so together you can eliminate all sorts of errors, spurious correlations, and whatever. And by adding first order building blocks and so on, you can also achieve higher levels of integration and generality at the second order level compared to the first one. Unfortunately, I don't have time to explain this in detail. I would have very much more to say, but I would conclude maybe with a short bridge to the presentation which Stuart will give in terms of reflexivity. Maybe it's useful to distinguish between 3 different types of reflexivity. The first one is a reflexivity in scientific building blocks. That's in like patterns of patterns, theories of theories. This is based on the reentry operation, and this creates reflexivity in terms of problems and issue and these building blocks. The second type of reflexivity is reflexivity with respect to the observer and re-entering into his or her observations, and this is what Stuart will be talking very soon. And then there is this environmental reflexivity between an observer and society, between society and ideas, and also what George Soros has there. It belongs to this category of environmental reflexivity, and with these outlooks on different types of reflexivity, I would like to conclude my presentation. Maybe to the last sentence, a small short aphorism. First order science, the science of exploring the world. Second order science, the science of reflecting on these explorations. Thank you.
Questions for
Yes, yeah.
we'll put all this stuff up. Questions for Karl while I'm getting my slides up.
Integrated is one of my favorite words, and particularly as it is applied to science. I think that the innovative edge in evolution witnessed the team that is working on the 3D printing of an artificial heart. Includes astrophysicists, physicists, and biologists, and blah, blah, all these people. I don't see that here in the second order science definition, and I expect it to, which is why I came.
You saw it very briefly in this. I moved here to the black carpet. You saw it very briefly when I talked about different types of re-entries. So I'll give you a concrete example. I was organizing a program at the University of Ljubljana. And the common theme was rare events. So rare events occur, rare events and power law distributions. This is something which you find in, for example, scientific quotations have this power law distribution. You have very few articles which are quoted over there. And so basically several faculties were part of this program. And we were on our way to address a second order issue, namely the question of generative mechanism. Each of these distributions has a generative mechanism. So in terms of scientific quotations, in terms of earthquakes, in terms of financial markets, and there are models around it, which somehow are able to capture this type of generative mechanism which produces this distribution. So you have all different disciplines: earth sciences, finance, social sciences, and so on. They all deal with this problem. And the second order problem is, can we come up with some generative mechanism which is behind or below the different generative mechanisms used in disciplines. So you have an extremely challenging, extremely integrative research question, and it's fascinating to work along this such a trajectory.
Would you say that Wolfram's new kind of science is a part of this exercise? Generating
he could be made part of this exercise. But there were other candidates as well, which we found, and then there were financial difficulties and the program had to stop, but it was fascinating.